class, welcome to EdVantage. My name is Dr. Scott Adamson, and today we're going to take a journey through the idea of trigonometry. You've probably seen at some point in your mathematical career things like sines and cosines and tangents, but do you really know what they are? Here's what they really are. Join with me here to examine this circle. This is supposed to be a circle, use your imagination, with a radius length of 1. That is, this is 1 unit, this is 1 unit, this is 1 unit. In other words, we call this a unit circle. I would like you to imagine I would rotate an angle amount, say to here. So I'm going to call this angle theta. And I'm going to connect that unit radius to the edge of my circle. And at the edge of my circle, I'm going to drop vertically down to the x-axis a length. I'm going to call that length the vertical height of that triangle. Now imagine, we're going to keep track of that vertical height as the angle theta changes. So for instance, if I rotated a really small angle and then drop that vertical height would be really small. In fact, if I don't rotate at all, if I just start right here and I don't rotate any angle measure, then that vertical height is going to be 0. In other words, in my graph over here, if my input quantity is the measure of the angle and my output quantity is the vertical height, if my angle measure is 0 degrees, then the vertical height is going to be 0. Now, as my angle increases, say to there, and then to there, and then to there, we could just kind of imagine that angle getting larger and larger and larger. And as it does, we're going to keep track of that vertical height. So that vertical height goes from 0 to a little bit, to big, to bigger, and when the angle becomes 90 degrees, then that vertical height would be 1 full unit. So as the angle measure increases from 0 to 90 degrees, the output, the vertical height, is going to increase from 0 to 1 unit. Now what happens after that? As we move into quadrant 2, as it's called, say we have an angle like this. So the angle theta now is this angle. The vertical height is now this vertical height. So the vertical height went from really small, 0 in fact, to bigger, 1. Now the vertical heights are going to get smaller. In fact, if we rotate 180 degrees, the sort of triangle we would create would have a vertical height of 0. So as angle theta increases from 0 to 90 degrees, the measure of that vertical height is going to increase to 1. As the angle theta increases from 90 to 180 degrees, that angle measure is going to decrease back down to 0. Now what happens if we keep going? If we go into quadrant 3 here, so imagine, now when we make that vertical height, the vertical height is always going to go from the circle vertically to that horizontal or x-axis. From the circle to the horizontal axis. From the circle to the horizontal axis. Now this height, since it's below that horizontal axis, we're going to measure this height as a negative. Not that it's a weird negative height, but just that it's below, negative meaning below. So an angle of like 185 degrees would produce a vertical height of a relatively small negative amount. And then as that angle progresses through quadrant 3, that vertical height is going to become larger and larger in the negative direction. And in fact, if we do a 270 degree angle, that vertical height is going to be now -1. So as theta increases to 270 degrees, our angle measures are now going to be in the negative amount until we get to 270, where the vertical height will measure -1. And then what happens as we run through quadrant 4? In quadrant 4, we're also going to see vertical heights that are on the negative side of the scale. They're going to start relatively large, and as that angle rotates to complete one complete revolution, to get to 360 degrees, that vertical height is going to get smaller and smaller and smaller and smaller and smaller until, can you imagine, like a 359-degree angle is going to be like this, and the vertical height's going to be pretty small. So we're going to come back up to 0. So what we saw, you can kind of imagine this playing in your mind like a movie. As the angle increases, the vertical height increases. As that angle continues to increase, that vertical height decreases. As that angle increases, the vertical height's now on the negative side and getting more negative. And then as we go through that last quadrant, that vertical height's going to again come back to 0. So we might imagine something like this. But what's it really going to look like? Well, it's really going to look like this. And I just want to take a minute to convince you that we don't have a linear situation. I want you to just get a little bit of sense of why I draw this in sort of a curved fashion. Let's take a look at this. Oh, first, let me tell you this. This vertical height has a name. We call it the sine of theta. When you see the sine of theta, what you should be thinking about is the measure of those vertical heights as theta increases. So we're going to take a look at just a few instances. Let's look at like 0, 10, 20, and 30 degrees. And then we'll jump ahead and we'll look at 70, 80, and 90 degrees. Just to see how are those vertical heights changing as the angle measure increases. Now make sure your calculator is in degree mode, and let's see what happens. Sine of 0 is, of course, 0. Sine of 10 turns out to be about 0.17. The height of that vertical leg there is about 0.17 units at 10 degrees. At 20 degrees, it doubles to 0.34 nearly. And at 30 degrees, we're up to 0.5. So in here, the increase is rather dramatic, relatively speaking, as you're about to see. But as we get near 90 degrees, the rate of change is much less. We start to curve there because look what happens at 70, 80, 90 degrees. At 70 degrees, we have a 0.94. At 80 degrees, we have a 0.98. And then at 90 degrees, we're up to 1. And so the changes there are very, very minute, relatively speaking. And so we do have this curved nature. I encourage you to explore what happens between 90 and 180, or 180 and 270, or 270 and 360 to make sense of the behavior of this graph. So we can do a very similar analysis, but instead of thinking about those vertical legs of those triangles, let's now think about the horizontal leg. That is, imagine again an angle theta, but instead of this vertical leg called the sine of theta, let's now think about this horizontal leg right here. So if you were to rotate an angle theta, create the right triangle, we would now think about this length. So we're going to think about the horizontal length as the angle theta changes. So imagine with me, first, we don't rotate at all. If we don't rotate at all, that horizontal length is going to be the 1 unit. So if we input an angle measure of 0 degrees, that is, don't even rotate anywhere yet, then that horizontal length is now going to be 1. Now, as theta increases, if we rotate, say, to here, notice the horizontal length gets a little shorter. And if we rotate to here, now we're thinking about this angle, the horizontal length is even shorter. And if we go to here and think about this angle, the horizontal length is even shorter. And if we get to 90 degrees, the horizontal length is going to be 0. So as we progress from 0 to 90 degrees, the horizontal length is going to go from 1 to 0. Now let's jump to quadrant 2. Likewise, as we think about the angle increasing, let's go all the way around to here. We're going to drop that vertical leg down, but this time we're going to think about this length. Now, negative, because we're on the negative side of the scale here, we're going to account for this as being a negative quantity. Not in any weird way, it still measures some quantity, but the negative just says we're on the left side now of the circle. So this would be a negative something. So imagine that horizontal leg as the angle progresses. It's going to be 0, and for just barely past 90, that horizontal length is going to be smaller, and then it's going to get bigger and bigger and bigger and bigger. In fact, by the time you get to 180 degrees, that horizontal length is going to be 1 unit, but to the left, so -1. So when we get to 180, our measurements on that horizontal length are going to increase to negative, left side, to negative 1. What happens here in the third quadrant? Imagine the angle theta. We're just playing this movie in your mind of this angle rotation to 180, and then now we're going to progress around to 270. So we're thinking about angles like in here, and we're thinking about that horizontal length. So as the angle increases towards 270, the horizontal length is going to get smaller and smaller and smaller. And in fact, at 270, the length is going to be back to 0. And on the negative side of the scale, so all negative quantities as we graph from 180 to 270 degrees. And then as we rotate into the fourth quadrant, think about an angle like this. Like we're going to go all the way around past 270 and get to this angle measure theta. We're going to create that right triangle. But now we're thinking about this horizontal leg. So the horizontal leg is going to grow until we go a full 360, where that horizontal leg will be back to 1. And so again, what we see is that decrease to 90, to negative 1, back up to 0, and then it's going to, after one complete revolution, be back at 360. And again, like we saw over here, we're not going to see any linear behavior. It's going to be curvy, and that curviness is due to this fact. If we now think about some values of theta in here for this quantity, which by the way has a name, this horizontal length is called the cosine of theta. When you see the cosine of theta, just think about the length of that horizontal leg. So let's say we want to measure the cosine of theta for, again, 0, 10, 20, 30, just to get an idea. And then we'll look at 70, 80, and 90 degrees, and we'll see how is the behavior here. So cosine of 0 was 1. Cosine of 10 is about 0.98. Cosine of 20, about 0.94. Cosine of 30 is about 0.87. So initially in here, for those first 10, 20, 30 degrees, the increase or the drop is not that significant. But what happens as we get into 70, 80, and 90? At 70, we've got a 0.34. At an 80, we've got a 0.17. At a 90, we've got 0. So relatively speaking, closer to 90 degrees is where we see the drop-off more stark than we saw it initially. So the graph is, again, curvy. And if we investigate those things in here, we'll see a greater rate of change here than we see here. We'll see a greater rate of change in here than we see up here. I encourage you, take a look at what happens at all the different angle measures.